So you'll need to wear goggles, but there's plenty of goggles there. So if you don't want to buy your own pair of goggles, there's plenty of goggles there. You can even take them like into the, you can scrub them up a little bit if you want to, but you'll need to wear goggles. And then Friday we'll be starting in on the numbers part of chemistry, and so bring your calculators that you want to use on your test. So this is where I think we left off. Been talking about matter. Matter can either be a pure substance or a mixture, and you kind of just take it. Okay, pure substance and mixture. Okay, and I'm going to talk about physical change and chemical change, and they kind of go along with physical property and chemical property. Okay, so if you take matter and you say that matter and it has changed, but it's been a physical change, then that means like on the molecular level, it's still the same stuff. Okay, you don't have any different substances. You don't have any different molecules or atoms. You're not breaking any chemical bonds or forming any chemical bonds. Okay, but sometimes physical changes can be, they look like they're a big hairy deal, but on the, again, the atomic level, it's still the same stuff. Okay, so physical changes, no new substances are formed. So examples of physical changes, and we're going to spend a fair bit of time talking about the whole solid, liquid, gas sort of thing. But a good example of just a physical change is when something kind of morphs between those three physical phases. Okay, it's still water, it's still iodine, it's still carbon dioxide, even if it solidifies. Okay. Another one is if you take matter and you just simply kind of crush it or kind of grind it, it's still the same stuff. You're not breaking any chemical bonds or forming any chemical bonds. Dissolving could go either way. Now, if you take salt, a bunch of salt, and dissolve it in water, you could get your salt back if you just evaporate it off the water. So actually the salt is remaining salt, even though it's dissolved in water. The other day, though, we saw a little video with lithium that went, okay? And in that case, the lithium dissolved, but it also expelled a gas, which is hydrogen gas. Okay, new substances were formed in that case. Okay, so dissolving could actually go either way, physical or chemical change. So here's the three physical phases of matter: solid, liquid, and gas. And you guys told me which has the most kinetic energy, which one's moving the fastest? The gas, exactly. And here in a minute, we're going to talk about something called intermolecular bonds. So I think we might have, sometimes I hit it a couple times, but basically over here in its gaseous state, there are no bonds, no bonds. And I'm going to call those no intermolecular, IM for intermolecular bonds. And over here in its solid state, we have lots of IM bonds. Yeah, I think we did talk about this, didn't we? Because here's this little table that we looked at before. Okay, and you guys did a homework where you basically kind of said these phases of matter, if something's a gas, for instance, its size is indefinite, and if it's a gas, its shape is indefinite. Okay, it has no intermolecular bonds and a high degree has a lot of kinetic energy. And the kind of the opposite is true for solids with regard to intermolecular bonding and energy. So when we talk about IM forces, intermolecular forces, thank you, it could be forces that are connecting repeating units like molecules, or it could be the forces that are connecting ions. So this is my IM, intermolecular bonds. But I started out this by saying, what is a physical change? So a physical change, if you break those intermolecular bonds, that's cool. That's still a physical change. Breaking those intermolecular bonds, or if those bonds are formed, that's still, you still have the same stuff. So if we line up the three physical phases, solid, liquid, and gas, it probably looks something like this with regard to those intermolecular bonds. If we go from left to right, okay, solid to liquid and liquid to gas, we're breaking bonds. Okay? If we go from left to right, we are breaking bonds. But the type of bonds we're breaking are intermolecular bonds. No chemical bonds are broken. And if we go from gas to liquid, we would call that condensation. And if we go from liquid to solid, what do we call that? What do we say when water goes from liquid to solid? Freezing, yep. Yep. Okay. In those cases, actually, intermolecular bonds are forming. Intermolecular bonds are forming. Cool. Well, in tomorrow's lab, these phrases might come in handy. Okay. So, endothermic and exothermic. You probably see the thermic as maybe heat, thermic heat, okay? Well, heat is a type of energy. Endo, I usually think of in, okay? Endo means in. So basically, if we say something is endothermic, we need to put endo in, we need to put heat in or put energy in. So if I were going to ask you, which of these from left to right or from right to left do you put energy in, you'd probably say from left to right. You put energy in, and you'd be right. If you take an ice cube, you add energy, it's going to melt. If you take water, you add energy, it's going to vaporize, okay? Not as intuitive is kind of this other direction. Okay, exothermic means energy is put out. So really, gas to a liquid. Really, for instance, when water vapor goes ahead and liquefies, a lot of energy is released. Okay, really when liquid water solidifies, energy is released then too. All right, so that whole energy put in, energy taken out kind of goes with this. Energy put in from left to right broke those intermolecular bonds. So it takes energy to break bonds. Actually, it takes energy to break chemical bonds too, but these are intermolecular bonds connecting large chunks of matter. And when bonds are formed, that was in this case when you're going from right back to left again, energy is released. All right. So physical phase changes. Something goes from a solid to liquid, we call that melting. Something goes from a liquid to a gas. There's two words for that. We could call it vaporization or evaporation. These would be putting energy in. And then if something goes from a liquid to solid, just like Jessica said, we call that freezing. And then one's last option is when something goes from a gas to a liquid, we call that condensation. And these we have to add energy. So it's endothermic. And here, okay, energy is released. Call that exothermic. Exiting, energy is released. All right. Again, showing that no molecules are harmed during evaporation. So here we see those cute little Mickey Mouse things. Those are water molecules, H2O molecules. And there you see it in its liquid state and its gaseous state. Endothermic. Now, there are some important times when matter skips the liquid stage. It goes either straight from a solid to a gas. Okay, we call that sublimation for sure. And sometimes it goes from a gas directly to a solid when it cools down. It skips the liquid state from gas directly to a solid. And we call that either sublimation or deposition. I kind of like that better. So here's an example. Just to kind of recap, endothermic means heat put in. So you would tell me between the three physical phases, you're going to have to add heat to get something from a solid to a liquid, that's called melting, or to get something from a liquid to a gas, that's called evaporation, or like we saw a minute ago with the I2, to get it to sublime. Okay, those are endothermic processes. Endothermic processes are, in this case, where bonds are being broken. Bonds are being formed in these, and energy is released when liquid goes to a solid, it's in freezing, or when gas goes to a liquid, it's in condensation, or when a gas goes right to a solid. I like to call that deposition. So, all right. So again, it takes energy to break bonds, and when bonds are formed, energy is released. All right. So that was all physical changes. Okay. No new substances are formed. Now, chemical changes, you get something new out of it, and sometimes it's not obvious that you got new substances are formed. So let's see if it looks like a new substance is formed here. Now, some of you are already kind of familiar with this idea. When we describe a chemical change, we actually can describe it in terms of the chemical reaction. Okay, and here's a chemical reaction up here. You read described in terms using a chemical equation. So you read chemical equations for chemical reactions from left to right. So basically, you're starting with this. Okay, and you are ending with this. And the thing that separates them, of course, is the reaction arrow. So right away, if somebody kind of gives you that description of some sort of chemical reaction in terms of an equation like that, kind of from left to right, it's a sentence, okay, they're saying that you definitely have new things over here. But again, it's not always so obvious. Okay. The new thing is the PCl3. What we started with was P4 and Cl2. Those 6 and the 4 we'll talk about later. But let's. Okay. I think we'll skip this for now. So I think when we talked about properties, physical and chemical properties the other day, I think we talked about when something rusts, that's an example of a chemical property, the fact that something can rust, because what rust is basically oxidation. So they're trying to show you rust here. So the silver up here is pure iron atoms, and here the silver with the red is iron oxide. Okay. So a chemical change has occurred. Here's a butane lighter. The next slide actually shows it with a fire going in it. But butane, is this right? Butane is C4H. Anyway, it's got 4 hydrogens. Let's see. 2, 4, 6, 8. Okay, 10. So it's C4H10. So these are little butane atoms, or excuse me, butane molecules. And actually, butane is another example of something that wants to be a gas at normal temperatures and pressures. So what they do is they liquefy butane, and they do that by pressurizing it and putting it in your little lighter. So it's a liquid in your lighter. But when you open the vent, basically it's all bets are off. Kind of the high pressure in here kind of interacts with the lower pressure out here, and it sends the material out in its gaseous state. So when you open it, basically you have gaseous butane coming here. Okay, so there's a liquid here. Notice here it's probably a gas. If you open up the little thing, the gas squirts out. So does this look like this slide, the caption says, this is an example of a physical change. Physical change. No butane molecules were affected.
So when you go to light a lighter, above the flame, if you're like holding it up and you're looking at the flame, is that what the gas is that haziness above the flame that you kind of see but not really more
Probably. The haziness that you see kind of above it that looks kind of transparent, and we'll see it when we'll see that same haziness when we use Bunsen burners in the chem lab.
Yeah, you see it like campfires and stuff too.
That is probably, what's happening is the air directly above that flame is really hot, and that hot air interacts with light differently than the normal temperature air. And so actually that it's causing what we call refraction. So it's a temperature thing and refraction. So it kind of makes it look watery and kind of like that.
Yeah.
But kind of along those lines, if you didn't light it and you just held it open, and if you did see some haze, then that would be your vapor. Yeah, your butane vapor. So then if you strike it, you can go ahead and get a chemical reaction to occur. You know, you see fire, you know that's some sort of energy, some sort of chemical reaction is going on. Anytime you burn, normal burning, you end up giving out normal burning of a fuel like this, hydrocarbon, you end up getting, like the slide says, water. Here's our water molecules, and carbon dioxide, okay? So basically what we have here is we have C4H10 reacting with O2 to form CO2, carbon dioxide, and H2O. Okay. One of the things I guess I would fault them for is they don't really show the butane, they don't show the oxygen, they don't show the O2, but that actually is in the mix there. Okay, so we have new substances out the flame. Chemical change. Burning is always a chemical change. And I wanted to make a note that all this stuff we've been talking about before with properties and now changes, you will have a section on your first unit exam that kind of, like your homework, that asks, can you tell me whether this is a physical or chemical change? Is this intensive or extensive property? Okay. So, no surprises there. So this looks all fancy and all that, but actually this is again a way to actually physically separate two or more liquids. It's called distillation. So it kind of starts over here. The business end is on the left. Okay. It's a physical change, type of physical separation, so no chemical bonds are broken, no new substances are formed. Basically, if you have two things that have different boiling point temperatures, this works real well. Okay, so over here, what you do is you have your mixture in there, okay, and let's just say that you are applying heat so that the liquid, let's say you have water, let's say you have two things, one thing that boils at 100 degrees Celsius and another thing that boils at 150 degrees Celsius. Okay, that's really nice because there's like 50 degrees between them. So does this make sense that the first one, the 100 degrees Celsius one, the first one actually is going to go ahead and boil first. It's going to go from a liquid to a gas. And then this part, all this does is to help the condensation process, okay, of your gas. This is just a glass tube on the inside. On the outside is basically a way that you could put up water, cooling water. So you put cold water here, and it comes out here into your sink, and it's just a cooling jacket, okay? The business end is on the inside. So basically it's a way to let that 100-degree vapor go up there and condense and roll down into your receptacle flame, okay? A cool thing, and we talk more about this in general chemistry, is if you have two substances like that and you're applying heat, the first one's going to boil, 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 and the second one will just sit there forever, and your temperature will basically plateau at the boiling point temperature. It won't move up until basically all of that fraction, what we say, has come over. Okay, when that's gone up, then your temperature is going to start creeping up to push in that 150 degrees Celsius, and then your other one would come over. And if you have three components, okay.
Even homemade distilleries in chemistry.
Homemade distilleries?
Yeah.
Did they work?
Yeah.
Cool. Did you test
mine
the?
did, not everyone's did, but.
Well, that's all that counts. Did you test the stuff on the other side, how pure it was?
Mm-hmm.
Very good.
Yeah, it was like desalination.
Very
It
nice.
worked really well. I felt like I was on moonshiners. It was awful.
If you take like a distillery and for like example, I guess, would the alcohol be the more volatile liquid?
Yeah.
The mixture of liquids, then what would it be? I don't know anything about moonshining at all, but what is it trying to separate out from the alcohol? I don't know if you know.
The
Because like,
You
wood
don't,
grain.
if, when you do it, you like purify the alcohol, you know, like when you get, I don't know.
Like the initial stuff, you get the alcohol and you want to, just leave the ingredients over here.
Yeah.
So the alcohol's more volatile. The things that are probably
That's
water.
what makes it like a higher proof,
Like
because you're getting out just the
additives.
alcohol, yeah.
They leave the other additives behind.
Yeah, exactly. Alcohols forms what it's been a while, but forms what they call an azeotrope. So it means that you can only get it so pure in distillation. But, yeah. Well, I'm glad to know we have some moonshiners in here. Yeah. But can you see where this is all just physical? We're applying heat and all that, but we're trying to make use of the differences in the boiling point temperatures. Good. This is also physical change. Basically, again, you could take a mixture like this, and let's just say you had sand and water. That's pretty easy. Sand and water, the sand would kind of settle down at the bottom of your Erlenmeyer flask, and you could, what we say, kind of decant off the water, but at the very end, you could go ahead and throw it into a filter. And you could use, this is a funnel, like you guys have in your drawers, but if we have these little round papers, and actually we can line this with a little bit of paper, and go ahead and collect our sand and whatever. So again, no molecules were harmed in this sort of process. All right, seems like you guys, do you have the answers to these? No, you don't, okay. Let's see, first one. Now these are changes. Is it a physical change or chemical change? So physical change would mean no new substances are formed. A chemical change means that new substances are formed. And sometimes I say it's a chemical change if you can't undo it, okay? So with that in mind, what if you had a purple shirt, you got bleach on it, and now it's no longer purple, it's pink? It is a chemical change, yep. Why would you say chemical? What's
I had purple sheets, and I spilled bleach all over my purple sheets, so now there's just a big pink stain.
There you go. It is a chemical
And
change.
there's no going back after you do that.
Could you get it back to being purple again?
If you dyed it.
If you dyed it, yeah. And what is dyeing? Probably
Chemical.
a chemical change, a chemical reaction. So yeah, you can undo it, but not with another chemical change. So when you exhale on these cold days, you see your breath, and basically what's happening is water vapor from your lungs is going from vapor to condensing, okay, to liquid. So it's a physical change, yep. Yep. The next one is plants convert or use carbon dioxide in photosynthesis to make sugar. Chemical change, yep. New substances are formed, yes. And what about solid butter liquefying? It's physical. Why is it physical?
There's not much changing other than
It's still butter.
It's still butter, yep.
It's just not good butter.
unless it's on toast.
Maybe
I guess
so.
you could do that. Put a piece of toast outside, put your butter on it, just wait a couple minutes, go out and get your toast, I guess.
Maybe so. Is that it? Is that the last one?
Yeah.
Okay, good. Okay. So this is the last slide, and we'll get to the assignment slide, but so when you're looking for things to review to get ready for your unit exam, your first unit exam in here, just kind of look at this slide, and it kind of summarizes things we've been talking about. So these will be due on Friday. It's Friday already. I'll take a quick look at these. No. Okay. So 41 and 42 go together, and classify these as a physical or chemical change. So just to reemphasize, chemical change is something new is formed, and physical change is the same stuff at the molecular level. So those would be good. And then the next two go together. I think you guys will do fine. The scenario with 43 is you have a block of aluminum and you're going to grind it and then you're going to ignite it. And then it bursts into flames and you have smoke also associated. So when you just grind it, is that a chemical or physical change? And then when you ignite it, is that a chemical or physical change? So 43, you have graphite now, and you break it into little pieces, and then you ignite it. You are some sort of pyro. And then you're supposed to say, when you break it up in tiny pieces, is that a physical or chemical change? And then when you ignite it, is that a physical or chemical change? I didn't know that, I guess graphite.
I was gonna ask that.
What's that?
This is flammable?
I'm sorry.
This is flammable?
Yeah, I don't know. I guess if you it's not yeah, I wouldn't think that lead like that is flammable. You guys know that lead is really carbon and graphite.
Yeah.
We should try that. I mean, that's the side of a little experiment I could do. Take a little bit of that.
Is actual lead flammable?
No, I wouldn't think lead would oxidize, like catch on fire. But that sounds like something to Google, because I know that like if you have a hydrocarbon like the butane, carbon with hydrogen, that is flammable. I just thought regular carbon, I didn't think it was very
Find
flammable.
out. Okay, we wanna know if actual lead is flammable.
We do.
Is graphite a harmless kind of
Graphite?
substance, I guess?
Yeah, I know, like if you